Hello again everyone, welcome back to ptet.chemistry channel. So my name is Dr. On, and in this tutorial video I'll go through these 9701 Cambridge International A-level exams for the 16 to 18 years old chemistry curriculum. This is for a slightly older syllabus. This is June 15. Oops, I made a mistake. This is actually supposed to be November 15th, paper 2-1. So it was from the previous syllabus, so some of the questions within this particular exam paper might no longer be relevant, and I will point it out throughout this tutorial video that are no longer relevant or that have been adjusted slightly to mirror the changes in the new syllabus. Okay, so let's get started. In this first question, we have atomic structure kind of question. This is typical from O-level or IGCSE level chemistry as well. So filling in the table in terms of the relative masses as well as relative charges, we know that the actual charge of a proton is not +1, it's actually a very small number. We also know that the actual mass of protons, electrons, neutrons are not this kind of whole number, but they are actually a number with 10 to the power negative 20 something, 30 something for the electrons. So they are really small masses. These are simply the ratio of the masses and the ratio of the charges. The fact that this one has a 0 charge, so only one out of the 3 particles are uncharged, that is going to be neutrons. Make sure you can spell them properly, Neutron. Neutron has the same mass as protons. They are the heavy masses concentrated in the nucleus of an atom. Together, neutrons and protons are what you call nucleons, and this thing, which has very small mass in comparison with the neutron and the protons, is around 2,000 times lighter. I never really remember this exact number. I always think about electrons being about 2,000 times lighter, therefore give or take around 1/2000. There's electron with a -1 charge and a proton with a +1 charge. Charges must have plus or negative unless when it's 0, so we're going to put in the plus and negative for these two particular species for that easy 3 marks to start off this question. Question 2, we have this relative atomic mass. The definition is in the syllabus. Of course, you're expected to know the definition of relative atomic mass together with relative isotopic, relative molecular, as well as relative formula mass. They are all stated in the syllabus for AS chemistry. For relative atomic mass is to do with the average mass of all the isotopes of the element, and then this is relative to 1/12 the mass of an atom of carbon-12. The fact that we are seeing this is element X mass spectrum, so on the x-axis we have mass over charge. Everything that passes through the mass spec will have a charge. If you don't have a charge, you won't see it, but this is from an element, so this element contains only 1 type of atoms, but there are 1, 2, 3, 4, and 5. So the fact that there are 5 lines means there are 5 isotopes of this element, and this element is element X. Some of them are present in a greater abundance, some of them are present in much smaller abundance. The fact that you have a lot of these isotopes with mass 80 means that your relative atomic mass is supposed to come down close to around 80 there. As expected, they do want you to define this particular term. For 3 marks, there are more lines for the relative atomic mass than the isotope. I would think the distribution of marks is supposed to be like 2 and 1. So Cambridge doesn't give out half marks. So you either get whole number or you get lesser than a whole number kind of marks. These are all stated in the syllabus as well. So relative atomic mass is defined as the average. So you must have the term average. It's not enough to just have keywords. This is average mass of all the isotopes. So an element can have more than 1 isotope, obviously, of the element. And this is in comparison, or this is relative to, or compared to the mass, compared to 1/12 times the mass of an atom, meaning 1 atom of carbon-12 isotope. So carbon-12 can be written as carbon-12. I prefer to write symbol where the 12 is on the top left because that's the mass number, that's the nuclear number, that's the meaning of carbon-12 there. Isotopes, they are referring to atoms of the same element. So they are different atoms, but they are for the same element. So what is different about their atomic structure? It's going to be same number of protons, so with the same number of protons, but different number of neutrons there. So the fact that you have different number of neutrons, so the number of protons plus the number of neutrons will give you the mass number or the nuclear number, and therefore you have different mass number and different nuclear number as a result of these. They don't mention about the number of electrons in here, but the fact that you are atoms, and if you have the same number of protons, your number of electrons must be the same as a result of atoms being uncharged overall. Now the next one is a calculation question. You're going to give your final answer to 2 decimal places and suggest the identity of x. Suggesting there, you have to refer to periodic table for the relative atomic mass value that has this particular value that you're going to calculate out. So let's have a look at our table. So I'll probably set up my formula here and then just copy paste it onto the next page. So 0.89% times the mass 74. So the percentage abundance times the mass number, and then I have to add them up all together. So 9.37 times 76 plus 7.63 times 77 plus 23.77 times 78. I was wrong. There's not just 5 isotopes. 1, 2, 3, 4, 5, 6. There are 1, 2, 3, 4, 5, 6. I missed one just now because it has such a small percentage abundance there. But just to be careful about this kind of thing. Running out of space there for my working, but no worries, I can easily move my things around. You can't on your actual paper when you'll be writing with ink, so you need to be careful and plan carefully. If you have to, you can write a second row as long as your working is clearly laid out, because that is what you can do as a student. And the sum of the percentages, these are percentage. Sum of percentage is out of 100%, and make sure whatever you do, you use bracket very, very wisely. So I'm just going to copy paste that. So I'm going to cut that, and I'm just going to go to the next page and paste it here. So my working seems a bit long because of all that thing. Seems like only 2 marks. You could probably have just, press a calculator and you just write down the numerator and denominator. So 0.89 times 74 plus 9.37 times 76 plus 7.63 times 77 plus 23.77. Oh gosh, okay, I made a mistake with my calculator. So you gotta be very careful that you are keying in the right stuff. I better stop talking. As I'm talking, I might make a mistake again, and I don't want to waste time in a real exam. So I got 7904.21 divided by 100. I could roughly tell my answer is correct because my mass number is very close to 79 and very close to 80 and also 78, where I have a lot of 80 and a lot of 78. So it makes sense the average is give or take around that region. So 2 decimal place, so 79.04, 2 decimal place as required in the question. Oops, that should be the AR value. So straight onto your data booklet and have a look in your periodic table. So 79, look for the mass number. So 79.0, that looks to be element selenium. So selenium on my A-level periodic table has a relative atomic mass of 79.0, stated in the periodic table there. The next one, the element beryllium reacts with chlorine to form a single solid product, and this relative formula mass to 70. They use the term relative formula mass, but the actual calculation method is still the same thing as you calculate MR. You just sum up the relative atomic mass. It's just that relative formula mass has a particular definition with respect to the ionic compounds that are forming between the metal and the non-metal. As you know, the metallic character, even though it's group 6, or group 16 as you would know in the new syllabus, the metallic character increases down the group. Now calculate the molecular formula of this chloride. To work out the molecular formula, we're given the relative formula mass, the MR, but we can probably work out the empirical formula first. If you have this much chlorine, so therefore the percentage of tellurium is going to be the remaining percentage, meaning the difference, because you only have 2 elements. You have beryllium as well as chlorine, so this is 47.4% beryllium. So I'm going to work out the empirical formula, simplest ratio of atoms, okay, simplest whole number ratio of atoms. So I'm going to work out the mole there. So in terms of the mole, there's the mass, 400 gram, tellurium in group 6, just below your selenium. So 47.4 divided by 127.6 mass over AR, because I'm talking about atoms, simplest whole number ratio of atoms. Similarly for the chlorine, 52.6 divided by 35.5 and not 71, because I'm talking about the atom, simplest whole number ratio of the atoms. So press it onto calculator. So I get 0.371, and then the next one, well, obviously it's a lot of numbers. I'm not going to write all of them down. I'm just writing out a couple of decimal places. Now what I do is I want the simplest whole number ratio. So I have to divide by the smallest number. So 0.371 is the smallest number. And then 1.482 divided by 0.371. I get 3.99, and that is really close to 4. So what I can say is the empirical formula is going to be TeCl4. So what we know is the MR of the empirical formula times by a certain factor. This will give us the MR of molecular formula, something you will have done from your O-level as well as IGCSE there. So there's 270. I don't know what factor I need to multiply it by. Therefore, I have to find the MR, the empirical formula first. So tellurium is 127.6 plus 35.5 times by 4. I get 269.6, which is pretty much 270. So you can see that the factor is just 1. When you get a factor of 1, this is not molecular formula. It simply tells you that the actual number of atoms in one single molecule correspond to the empirical formula, the whole thing multiplied by 1. So what you have is TeCl4 empirical formula. The whole thing just have multiple of 1. So when you have the whole thing expanded, this is the actual number of atoms in one single molecule. That's the definition of molecular formula. Even year 9 O-level, GCSE and IGCSE students would know that that is the definition of molecular formula, actual number of atoms in one single molecule. Next thing, this chloride, TeCl4, it melts at 224 degrees Celsius, reacts vigorously with water. Think about the bonding and structure, and explain your reasoning. So the first bit, we're going to be thinking about things like just above beryllium, things like SCl4, which you don't really do, but what you do is you do group 14 or group 4 chloride, which you know about SiCl4, does react with water. I'm not saying silicon is above beryllium, but I'm saying that you know about period 3 chloride, and they give you SiO2 and HCl, balancing every single equation you write. This is what you call hydrolysis. So we also know that that reacts vigorously with water. You get a steamy white film. We also know that that is simple molecular. It's a liquid at room temperature and pressure. This one, even though it melts at 224 degrees Celsius, the fact that it does that and it does react with water, meaning to say it undergoes hydrolysis, and it doesn't just dissolve in water. Doesn't just dissolve in water, unlike your normal ionic compounds like sodium chloride. Salt just dissolve in water, right? So the type of bonding that we have here, the TeCl4 has simple covalent structure, or you can say simple molecular structure. They both mean the same thing, but I need to mention the bonding now. So I have covalent bond. So this is strong covalent bond between the beryllium as well as chlorine atoms. These are non-metal, well, they're considered as non-metal atoms, otherwise they wouldn't have formed covalent bonds between themselves like that, okay? And then explain your reasoning. So relatively low melting point, relatively low. I'm not saying it's very low, I'm not saying it's like negative. So it is still a solid at room temperature and pressure because you haven't melted at 25 degrees Celsius. Relatively low melting point suggests a simple structure, a simple covalent structure. Okay, because if you have a giant structure, could be giant metallic, but it cannot be giant metallic because it's a compound, could be giant ionic or giant covalent, you will have extremely high melting and boiling point. So what are we breaking here? We just break weak intermolecular forces between the molecule when we melt this simple covalent molecule. So intermolecular forces means between the molecule. Last but not least, I should really explain the other thing as well because this N reacts vigorously. So we can say TeCl4 hydrolyzes readily in water. It doesn't just dissolve in water, it hydrolyzes readily in water. So meaning to say TeCl, covalent bond, will break when you react with water. Okay, upon hydrolysis, we don't really have to specify the product, but there is a violent reaction as a result of the hydrolysis happening. Well, actually, we might have to, because they are asking for what happened when the TeCl4 reacts with water. I can draw inspiration from what I had done previously with the silicon tetrachloride, which is from group 14 chloride, which is your period 3 chemistry. Oops, not silicon, but then TeO2 perhaps, tellurium oxide, and what I get could be HCl, and 4 of that and 2 of that, suggest. So it's not in your syllabus, but it is based on something that you might be able to get from your syllabus, just like that. Now the next thing, these are chlorides of the third period chemistry, period 3 elements. So as I mentioned, silicon tetrachloride there, melting point, it's got very low because it's simple covalent structure. Now describe what you would see during the reaction between sodium and chlorine. This is not silicon and chlorine, but this is between sodium and chlorine. This is sodium metal, and then you have chlorine non-metal. Okay, so what you would see, well, sodium metal is not white in color. It's kind of like kind of dull color, I guess. When you cut it fresh, it's not reacting on water, so there's no water in here. Chlorine has a color. It's kind of pale green gas, but sodium chloride is a white color solid. So it's a white solid at room temperature and pressure. So as that form, you will see a white solid. But what will happen to the color of the non-metal? Well, this color will disappear as the chlorine reacts. And the sodium is a piece of metal, so you would lose the color of the metal itself, which, you know, when freshly cut, looks a bit grayish. So it will, I think they call it lustrous, but then the lustrous appearance of the alkaline metal will disappear as the sodium reacts. Okay, so as the sodium reacts, what we could say, the lustrous, I think that's the correct adjective, the lustrous shiny appearance from the freshly cut sodium will disappear. It will fade away, it will disappear as it reacts. Okay, also as the chlorine reacts, the chlorine exists as a Cl2 molecules. The pale green color, so it's a pale green gas. The pale green gas will fade in color. It gets lighter and lighter as it reacts. But last but not least, we also observe a white solid being formed. So this white solid is sodium chloride, but you do not see sodium chloride. You observe a white solid being formed, as it is a giant ionic lattice structure kind of solid. It has high melting point, and therefore it exists as a solid at room temperature and pressure there. Now in terms of the melting point, this comes down to structure and what bond you need to break. And you should also refer to the difference between the electronegativity. We know that electronegativity is the ability of an atom, is the power of an atom to attract the bonding electrons towards itself. So looking at this 2.2 and 3.1, so this is a bigger difference in electronegativity. So when you have bigger electronegativity difference, it kind of shift more towards the ionic bond kind of spectrum, whereas when you have small electronegativity difference, so things like non-metal and non-metal, they prefer to form covalent bond. So in terms of the explanation, I can say that the smaller electronegativity difference, so they want us to refer to that, right? So I can say it's the smaller electronegativity difference between silicon and chlorine compared to. So you can have different way of explaining things. All I'm doing is I'm just outlining my thought processes here, okay? Compared to between sodium and chlorine means, so we are talking about the small electronegativity difference, means silicon and chlorine are more likely to form covalent bond. Whereas the bigger the difference in your electronegativity, something likes to lose, something likes to gain in terms of electrons, and therefore you would shift towards ionic. Okay, so in terms of the bigger difference, what else? You should refer to the difference. Okay, explain the difference in terms of their structure and bonding. So NaCl has giant ionic lattice structure, as you would know from your O-level stuff, your GCSE or your IGCSE knowledge as well. So we need to break. So melting NaCl needs to break very strong ionic bond or strong ionic bond, and this is between oppositely charged ions. So this is between Na plus and also Cl minus. In terms of the next one, the SiCl4 has a simple covalent structure or simple molecular structure, whichever one you prefer to use. So simple covalent structure or simple molecular structure is the same thing. We're talking about boiling. No, we're talking about melting point. So I guess I should think about melting as well. So melting SiCl4 only needs to break. So here is where your adjective is very, very important. This is your weak, and I have to specify my intermolecular forces, as that is something you have learned as London dispersion forces or van der Waals forces. London dispersion forces are the new terms they use in the new syllabus, but if you use van der Waals, you'll be accepted as well. And these things are non-polar, as it is a tetrahedral molecule with a symmetrical distribution of charges, because all the atoms around this tetrahedral geometry with zero lone pair, the dipoles cancel out despite the bond being polar, but the dipoles cancel out in this particular geometry. And these are weak van der Waals forces. These are between the molecules. Running out of space here, but let me just complete that. Between the molecules. In terms of the explanations for the electronegativity, I've only mentioned about the covalent bonds. I haven't mentioned anything about the ionic bonds, so I don't think I'll get the full marks yet. So when the electronegativity difference, when the metallic sodium and non-metallic chlorine has much bigger electronegativity difference, this will shift the bonding spectrum towards this shift the bonding spectrum towards being ionic. Then how in the world do we know whether it's ionic or covalent? You don't really. So bonding is a spectrum, like I said. So it's not like one specific value would tell everything. But in general, when you have a metal and a non-metal, in general, they prefer the ionic bond. And because towards the ionic bonding regime, and that is because the metal sodium prefers to lose electrons, so not very electronegative at all, whereas in this case your partner, which is the non-metal, which is the chlorine, it's much more electronegative than the metal. It prefers to gain the electrons, and because that is much more electronegative compared to the metal atom. Whereas when you have the silicon and the chlorine, they don't have much electronegativity difference, therefore they prefer to share electrons, so they just share electrons. For that, SiCl4, they share electrons instead, and therefore they form covalent bonds. I think that's probably enough already. So I mean, I've just tried to answer the question as best as I could. Structure and bonding, probably 1 mark and 1 mark. A lot more lines in here, probably the distribution of 2 marks here. That's why I don't think it's enough to just talk about the small electronegativity difference there. I should talk about why ionic, why covalent there in terms of the electronegativity difference. And there's something that are in the new syllabus as well, where they will provide you some electronegativity difference value. Where they'll provide you some electronegativity, and you probably have to do some calculations to work out the electronegativity difference and probably explain the bonding spectrum like that. So that's the end of this 20-mark inorganic chemistry question. So inorganic chemistry is about 1/3 of the whole AS chemistry. So you can expect these 20 marks to cover the whole of inorganic chemistry for this particular paper.